Let's talk about our paper, Tolerance-Guided Policy Learning for Adaptable and Transferrable Dedicated Industrial Insertion. So robots has been widely applied in manufacturing like computer communication and consumer electronics, though it still remains challenge for robots to handle dedicated insertions. For example, the assembly of an IC socket on a PCB board. The conventional model-based methods for insertion can achieve high performance, but require case-by-case tuning and have poor generalizability. Forming such a production line consumes a significant amount of time and resource. However, nowadays the accelerated pace of product innovation has significantly reduced the life cycle of a production line. This gap urges the assembly lines to be more flexible, and robots are required to be equipped with general insertion skills that cover a variety of tasks. While learning-based methods are promising to learn the skills, there are still two major challenges. How can we learn a diversified policy for multiple or even unseen tasks, and how to handle defects of workpieces like bent pins? To make our policy adapt to different tasks, in other words, workpieces, we introduced a tolerance model. Tolerance refers to the amount of spatial error or force error that is admissible for the insertion. We call the mathematical description of the tolerance as the tolerance model. It describes the peculiar dynamic properties of different insertion tasks. We then map the tolerance model to a low-dimensional task encoding for our network. In this way, the policy network can learn the underlying mapping between the tolerance model and the suitable strategies for different tasks. Even given a new task, the policy can infer the suitable strategy based on the task encoding. In real application, defects may deviate the real tolerance model from the default one and cause an insertion to fail. To compensate the defects, we build a probabilistic model. The model assumes a prior distribution of the real tolerance model, which may be parameterized according to factory data, and it leverages the previously failed insertion to update the distribution of tolerance model. From the updated distribution, we can infer the probability of insertion as a function of reference goals. Then we can choose the optimal goal and fit it into the policy to compensate the defects. This is how the system looks like when we introduce the compensation.
Our proposed policy is called tolerance-guided policy, which includes two parts: nominal policy, which is the green network in the figure, and tolerance embedding network, which is the green network in the figure. The nominal policy takes states and output actions. For the tolerance-guided policy, it takes low-dimension task encoding encoded by tolerance model as input to capture task specification. For the training process, we first train a green network. Then we fix the parameter in the green network and only update the parameter in the green network. Finally, our policy will know how to perform well in new and unseen environments. To train our networks, we introduced the generative adversarial imitation learning algorithm, namely RS-GAIL. RS-GAIL leverages both the IELTS optimality and IELTS effective exploration. By gradually increasing the weighted factor alpha, the learned policy will start from being similar to expert and finally converges to be optimal with regard to environment reward. We perform our experiment in an OpenAI gym simulator where we implement the insertion process as first our analytical dynamic equations. The matrices we use to reflect performance include reward, successful rate, number of steps, and number of collisions. Going to our results, our learning algorithm RS-GAIL gives smoother and more optimal trajectory over the training, outperforms the expert and imitation learning policies, and learn optimal policy under sparse rewards. For the evaluation performance on unseen environments, after training on 2x2 and 2x8 pins environments, our tolerance-guided policy outperforms the nominal policy, on the unseen new 2x4 pins environment. As a result, tolerance embedding enhances the transferability, generatability, and robustness of the learned policy. Given an environment where the workpiece has unknown defection, policy with probabilistic inference can update the desired target insertion posts from failure insertions and get good performance. That's all our presentation. Thanks for listening.